Welcome back to the last talk of the morning session. Today, we are very excited to have Merrill. He's a PhD student at NYU and is now at AI2. And he's done one of the first foundational works on trying to understand the representational power of transformers and connecting it to circuit complexity, formal methods, and so on. And I understood a lot about this space from reading papers by Will. So I'm really excited and to hear what he has to say about the expressivity through circuit complexity. And I think it'll summarize really well all the different approaches that Daniel Bigben Stock put together with Will's talk. So let's take it away, Will.
Cool. Thank you for the introduction. So I'm going to be talking today about basically a series of several papers using circuit complexity to think about the power and limitations of transformers. And this is largely joint work with Ashish Sabharwal, who's a research scientist at AI2. So one of the interesting things about language models and transformers in recent years is that people have started expecting a lot more from these models. So whereas in the past with maybe n-gram models, we wanted language models that were kind of like good predictors of coherent text. Now people want them to do computation or reasoning, if you prefer that term. So for example, you might want to frame a reasoning problem, like a graph connectivity problem to a transformer. Here I've given this very simple graph, and you can have a question like, is there a path from B to D? And in practice, what often happens with language models is even for some simple problems, the reasoning or computation can fail. So here, the model says there is a path from B to D, even though visually you can see very easily that there's no such path. So a fundamental question then, motivated by this, is what are the kinds of reasoning or computation that we can expect to be implementable in transformers? In some sense, that's one of the big questions of this workshop. And then also, I think one of the interesting aspects of this question is, are there some kinds of computations that are fundamentally difficult or hard to express in a transformer? And one way we can formalize this or think about this is in terms of characterizing the expressivity of the model. So the basic question is, what kind of computational problems can transformers fundamentally not express? And in this talk, I'm going to talk about, I guess, how we've identified some simple problems that transformers with a fixed but kind of arbitrarily large, but fixed with respect to the sequence length, depth, and size, can provably not express. And the tools to do this are largely based on circuit complexity. And one such example, turns out, is this graph connectivity problem that I showed in the last slide. So hopefully by the end of this talk, you can understand where this result comes from and how you can also apply this general framework to think about other problems as well. OK, so the goal of this line of research is we want an upper bound on the expressive power of transformers. And I'm going to clarify what these terms mean. I'm also using upper bound in maybe a slightly different sense than what people are thinking about here. So by expressive power, I mean the class of problems that transformer classifiers can solve with hand-designed weights. So we're basically abstracting away the learning process of the transformer and just saying, if we could pick the weights as however we want, what could we do? And by upper bound, I mean nothing about resources, but rather a set of problems that is a superset of all the problems transformers can express. So it's hard to precisely describe what transformers can do. So we're OK with a set that is a superset of everything transformers can do. And then if you combine these two things, logically, anything outside this upper bound class cannot be expressed by a transformer. So that's like the general way we're going to approach this. And as far as the specific contributions we have in this program, I'm first going to talk about some prior work before we started thinking about this that analyzed what are called hard attention transformers. So this is a simplified model of transformers that showed the circuit class AC0 is an upper bound. And then I'm going to move on to our first upper bound, which is TC0 as a kind of upper bound on this more generalized realistic model of soft attention transformers. And then I'm going to talk about the implications of this upper bound, how we can use this to actually come up with concrete problems that can't be expressed within transformers, such as graph connectivity. And finally, I'll talk about how we can overcome these expressivity limitations. So what are ways we can get transformers to express computation outside the class TC0? So here I'll talk about chain of thought, the method used by models like GPT-01, and then also whether other architectures can change the expressive power. So most concretely, we've thought a lot about state space models. Any questions before I start? OK. So before I dive into this, I want to talk a bit about prior work on the expressivity of RNNs. So there's a pretty rich literature on this before people started thinking about transformers. And generally, the approach people used to understand the power of RNNs was by relating them to classes in the Chomsky hierarchy, such as the regular languages, context-free grammars, so on. Unfortunately, this approach doesn't get you really far with transformers because transformers are a fundamentally different beast than automata or any of these other models of computation that build on automata. And the reason for that is really due to parallelism and lack of recurrence. So right, in transformers, we don't have any explicit recurrence. Oh, yes. I guess I just wanted to show some more of the foundational works, but there are. I mean, sure, there's a lot of work going back even to when RNNs were proposed. Like these are very close models. I agree. Yeah, in the 90s. Yeah, I guess that should be there too. I agree. No, I think that's good work. I guess yeah, I don't know.
The distinction, of course, is that the Turing machine, you have to use infinite precision, and all of these works are using finite precision.
Right.
So I thought you were drawing that distinction.
I mean, that is a distinction. I guess this more recent work, starting with the Weissedal paper, showed that if you restrict to the finite precision setting, you get reduced power compared to Turing machine.
So we should take finite precision as the key restriction in all of it.
I think so, finite or at least bounded. Yeah. Yeah. Any other questions? No. Okay. So I guess going back to this, so why don't transformers relate nicely to the Chomsky hierarchy? The fundamental problem is a lack of recurrence in the computation graph for the transformer, whereas all these classes in the Chomsky hierarchy kind of have a built-in recurrence because in the least expressive level, you still have a finite state machine. So if we want to actually meaningfully relate transformers to a hierarchy of problems in computer science, we need to look elsewhere. And that's why I guess we and other people started looking at this circuit complexity hierarchy. So we're going to relate transformers to circuits and then use that to draw insights about the types of computation that they can express. So that brings us on a detour into circuit complexity. I'm going to kind of describe some of the basic ideas with circuits very briefly. So circuits are a quite intuitive model of computation. They're basically a DAG where you have input nodes representing basically bits, and then you have internal nodes representing functions, so typically logical functions over these bits. And the idea is you just basically propagate the input values through these functions until you reach an answer at the last node. So for example, if we want to evaluate 0, 1, 1, we just assign these values to the input nodes. We compute the first level of functions, and then we go up the depth until we have evaluated the output of the circuit. Okay, and then there's two natural notions of complexity for these circuits. One is the size, which is just the number of non-input nodes. So here the size would be 3. And this corresponds kind of to the runtime of the circuit if you wanted to run it without any parallelism. So for example, if you wanted to simulate the circuit with a Turing machine, you would need to iterate all of these nodes sequentially, and the runtime would be roughly the size of the circuit. Another natural notion of complexity is the depth, which is the length of the longest path from the input to the output. So here the depth is 2, just like you describe the depth of a neural network. And this corresponds to the runtime with parallelism. So if we had an unlimited number of parallel processors and we wanted to execute this circuit, the best we could do is running everything at depth 1, then at depth 2, and so on. So those are circuits. You might notice that they take a fixed size input, but we want to be able to think about problems of unbounded length, I guess because we're talking about languages. So one slight detail I'm just going to talk about is we're actually talking about circuit families here, not circuits. So if you want to take in a sequence of inputs with a circuit, you need to technically have a sequence of circuits. And depending on the input length, you use a different circuit. So that's really what we're talking about rather than specific circuits. Okay, so the starting point for our work came from this existing line of work that was analyzing hard attention transformers. And one of the interesting insights there was that circuits were a quite useful tool. So this dates to this paper from Michael Hahn in 2019, which kind of used techniques from circuit complexity to analyze transformers. And then this was made kind of more general by Sophie Howe, Dana Anglin, and Robert Frank, where they actually showed a connection between transformers and the circuit class AC0. And AC0 is this class of circuits, or class of problems definable by circuits with constant depth, and polynomial size. So intuitively, you can think about this class as problems that can be parallelized to a very high, i.e. constant degree. So concretely, what polynomial size means is the size of the circuit can be very large. On inputs of length n, it can be any polynomial of n. So you could think about that as large, but kind of like attractively large. And then the depth of the circuit is constant or fixed with respect to n, meaning that no matter how long you make the input, there's some fixed depth that the circuit has. And that's where this parallelizable to a high degree comes from. And it's classically known that AC0 is a very limited complexity class. So I guess there's this famous result from the 80s where like functions like parity, so taking the XOR of a sequence of bits, can't be expressed in AC0. So I guess just to show what parity is, like this would be taking basically like 1, 0, 0 would be in parity, because if you take XOR of these bits, you get a 1, whereas 1, 0, 1 would not be. Another function that turns out to not be an AC0 is the majority function, which is really simple. You just take a sequence and you take a majority vote. Are there more ones or more zeros? Like this. So the result that was shown by this paper was that actually you can simulate a hard attention transformer in AC0. So what this means is that basically, what hard attention means, just to be more concrete, is that if you have an attention pattern, you need to put all of the probability mass onto a specific token. So you're basically doing some kind of retrieval rather than taking an actual weighted average across the tokens, which is how softmax is defined. So this is a simplifying assumption that is needed to obtain this result. And the implications of this, well, it shows that hard attention transformers are quite weak because they can't express these basic functions like parity or majority, which are like really simple types of computation. Like parity, you could express with a two-state finite state machine, for example. And in particular, this shows that hard attention transformers can't even recognize all the regular languages. But of course, this hard attention assumption is quite strong. And it doesn't allow uniform attention, which is where you spread the probability mass evenly across all the tokens. And in lots of like concurrent work, this has been shown to be a useful primitive if you want to think about how to write down algorithms inside transformers. So this is what uniform attention would look like. That motivated us basically to think about what if we generalize this to soft attention? Does this result still go through, or can we get an alternate result that goes through, but maybe with a weakened class? And just to show you that AC0 no longer is a valid upper bound for soft attention transformers, we can very easily compute majority, this problem that's outside AC0, with a one-layer transformer. So the way you do this is you basically take like a uniform attention head that averages the input values, and then you just threshold them against 0.5, and this will come out to be greater than 1 if and only if more than half of the inputs are greater than 1. So very directly with soft attention rather than hard attention, you can get around this AC0 upper bound. And our question then is, can we relax this upper bound and get something that still works using similar ideas? Any questions about this hard attention stuff before I continue? Okay. Yeah.
Is there a simple intuition for why for the earlier bound, which deals with AND or NOT gates? Because obviously, if you have the XOR gates, then you can do things like parity.
Yeah.
Constant depth. So, what's the intuition for hard attention corresponding to this particular class?
Yeah. So I guess it's pretty easy to show that you can simulate the MLPs with hard attention because they're basically like very local simple functions. The hard part is showing that you can simulate the hard attention operator. And one way to think about it is you're basically computing a maximum between a bunch of like a quadratic number of pairs. So it's possible to compute the maximum of like 2 items in AC0 quite easily. And you just need to do that n squared times. Like check, is this greater than that thing? And then you look at the item that is greater than everything else. And that's how you would simulate hard attention. Yeah. Any other questions? Okay.
And that in particular takes advantage of the very wide size allowable in AC0.
Exactly, right. Okay. So moving on to TC0 and soft attention. First going to define the model we're talking about, because I guess with hard attention, well, with soft attention, we need to do some kind of arithmetic over numbers, because we're not just retrieving a specific item, we're like actually computing averages of vectors. So the assumption we're going to make is that we're operating in log precision, meaning the arithmetic precision in the transformer gets at most log n precision on sequences of length n. And the reason we make this assumption is because we want to capture some kind of bounded precision regime. But finite precision turns out to be too restrictive, because you want to be able to represent different positions. And in order to do that, you need like something like log n bits. And also you want to be able to represent uniform attention weights, so like 1 over n. And in order to do that, you need something like log n bits. So that's why we choose this log n assumption. It turns out that you don't actually need to make this assumption to get these results to go through. But in our papers, we like generally have this in the title and so on. So I wanted to mention it. But you can relax this assumption and also prove that you can simulate a transformer in TC0. OK, so that brings us to the first result from this paper in 2022, which is where we showed that log precision transformers can be simulated by polynomial size, constant depth threshold circuit families. And another way to say this is they can only solve problems in the class non-uniform TC0. So what are these threshold circuits and TC0 as opposed to circuits in AC0? Well, basically, they're defined very similarly, like constant depth, polynomial size, but we're now allowed more expressive primitives. So we add this one primitive called maj, which is basically just an oracle for the majority function. So majority is this function that you can't compute in AC0. What happens if we just throw it in to the transformer and just allow it to be there as an additional gate? And that defines this class TC0, which is a straightforward extension of AC0 with majority. And automatically, we can see that TC0 will be more powerful than AC0 because it contains majority, a function which is not in AC0. So what are the implications of this? So I guess a similar takeaway to the AC0 result still goes through. Transformers can only express problems that are parallelizable to a very high degree, because this is a class that's defined by parallelism, just like AC0. The only difference is that the primitives we're allowed to use are more complicated within that parallel computation. And in some sense, this shouldn't be surprising, because transformers were designed to be a parallelizable architecture. But this is a way to very concretely capture that. And another interesting implication of this is that majority or counting, in some sense, capture all the additional power of soft attention versus hard attention, because all we have to do is throw that into the circuit definition, and suddenly we can capture soft attention. And this is actually similar to some of the results with RNNs, where one of the separations between LSTMs and RNNs is like these counter languages, so languages defined in terms of counting capabilities. However, this result, as stated, doesn't really give us concrete problems that transformers can't express, which is what I opened the talk with. So for that, we actually need to refine this result and give a uniform upper bound. In other words, we need to show that we can simulate transformers within a different version of TC0 that's uniform, meaning that as the circuits get larger, you can actually construct those circuits from the input length. If this is unclear, don't really worry about it. It's mainly just a technical condition, but it turns out to be important here. So in fact, we did show this. So we refined this original non-uniform proof to go through in the uniform case, which is not too difficult. And we can even actually refine this more. So there's different notions of uniformity. And if you make the result very, very uniform, it actually turns out to give you implications about logic. So not only are transformers expressible in uniform TC0, but they can actually be defined in a variant of first order logic as a corollary of this. So, yeah.
Exists, right? So I would have assumed you need to assume the uniformity rather than prove it.
You need to assume the uniformity.
Well, because it seemed like your transformer, the way you defined it, was an inherently non-uniform class, and so if you're giving a uniform simulation, you have to put in that assumption somewhere.
So I mean, transformers are actually a pretty uniform model of computation, because you just define the weights at one token. And if you want to extend to longer strings, you just copy the same weights to extend to longer strings. So the model is actually very naturally uniform, and that's why we're able to prove that it is uniform. I guess you need to capture those components of the structure in order to prove that, which was really like the difference from our earlier papers to our later ones. Does that make sense?
What about position encoding?
Yeah, good question. So positional encodings, I guess if you have learned positional encodings, that could be non-uniform. We're analyzing a model that has, I guess we assume that the positional encodings are uniform. So for example, we're assuming you're using some kind of like method that gives you positional encodings rather than learning them as parameters.
So they depend on the sequence length.
Yeah, yeah.
Yeah, am I being precise about this? So the positional encoding is always mapping to something which is a fixed polylog of n, correct? And it's a fixed function.
I mean, I guess like the most straightforward thing we assume, like with a causally masked transformer, you don't really need positional encodings. You can get away with just the beginning of sequence token.
Formally, yeah,
But
In practice, you can learn it that way. But
so do you do or do not use positional encodings in your theorems?
we make some assumptions that are basically like the function that maps from I to like encoding of I is like uniformly computable as a function of
And the size of the encoding?
as like yeah, basically it's computable in like log n space where n is the context length. Yeah. But that captures a lot of natural positional encodings. Okay, so I'm not going to talk more about this logic direction, but tomorrow David will present about connections between transformers and logic, and there's a lot of interesting like work beyond this there. So going back to the circuit view and this uniform PC0 upper bound, what do we learn from this? So the interesting thing about uniform circuit classes is that they fall into a natural hierarchy within polynomial time. So now we have AC0 and TC0, the uniform versions, and they form the base levels of this hierarchy of different types of problems. And you can think about these different levels in this hierarchy as capturing kind of how parallelizable is this problem. So at the bottom, you have AC0, which is very, very parallelizable. At the top, you have P, which is like computation that is very inherently sequential and hard to parallelize if you're like in the P-complete region at the top. And by placing transformers within TC0, we're basically putting them in the lower levels of this hierarchy, which means that they can't express the problems that are inherently sequential that are complete for the upper levels of the hierarchy. And of course, this is under kind of complexity assumptions. So basically, assuming this hierarchy doesn't collapse, that conclusion holds. But like if TC0 equals NC1, then this whole thing falls apart. So now I'm going to take you on like a tour of some of the classes in this hierarchy and explain some of the problems that fall in these different classes. And like by this logic, we know that transformers can't express these problems. So first, we can look to NC1, which is the class right above TC0. And unless TC0 equals NC1, we know that we can basically conclude that transformers and the regular languages are incomparable. So in one direction, we know transformers can clearly recognize some non-regular languages. So one example is this majority language that I showed you earlier. It's not regular because it involves counting. So that's one direction of incomparability. And in the other direction, under this TC0 not equals NC1 conjecture, some regular languages are outside TC0. So Bingbin mentioned this permutation composition S5 word problem task. That's one such language, as you can see in the figure. And an intuition here is that automata are very simple, but some of them are inherently recurrent. They require going through the input left to right. And that's why transformers can't express like these hard, inherently sequential automata. There are other problems that are NC1 complete that are interesting. So I guess I just mentioned this S5 problem, which is closely related to composing permutations. So for example, if you have lines of Python that do permutation composition, then you want to evaluate this code. That would be like kind of a practical realization of this S5 task that would be inexpressible in the worst case, at least. Another problem related to code evaluation is like evaluating compositional formulas. So if you have formulas that nest like plus and times, and you want to be able to read this formula and say what it evaluates to as like an integer, that would be inexpressible as well, because this is also NC1 complete. Yeah.
alphabets that are.
Yeah. So basically, you can define like if you want to define an output with like 10 bits, you can have 10 different circuits that share a lot of structure, but just like sparsely activate different output bits. So it's a bit messy to generalize to like non-binary outputs, but it is very much possible. So I guess both of these tasks are kind of related to code evaluation, and they're suggesting that at least in the worst case, some aspects of evaluating like Python code fundamentally are inexpressible by transformers. Although obviously the practical question of can models evaluate Python code is like somewhat removed from this worst case result.
So how do you prove a result like this that a transformer cannot solve this category of problems? Any specific technique for these kinds of proofs?
Yeah, so the specific technique was just showing this connection between transformers and TC0, the circuit class, and then like this actual result about code evaluation, we're just getting for free from the existing theory about circuits. So people know that this problem is likely not in TC0, and by making the connection to TC0, we know that transformers also can't express this problem. Any other questions? Yeah.
Do you have problems in TC0 minus transformers?
We have some conjectures. David might also talk more about this. No? Okay. But yeah, I guess one intuition is that transformers have kind of a quadratic size, whereas TC0 is defined with a polynomial size. So problems that require like maybe n to the 5th parallel computations probably can't fit in TC0, although the theory and circuit complexity on like hierarchies within TC0 is not fully worked out. So we can go one level up this hierarchy and find other problems. So if we go up to NL, non-deterministic log space, which is above NC1, a complete problem for this class is graph connectivity for directed graphs. And that's where this result I mentioned at the beginning of the talk came from. Basically, it's the same type of argument, but just for a more powerful class above TC0. And finally, we can go all the way up to polynomial time and look at problems that are complete for polynomial time, which intuitively are problems that are very hard to parallelize at all. So one example is linear programming or solving linear equalities over Boolean matrices. So this is p-complete, and therefore we can't express it. Another one is kind of in context, context-free recognition. So if I give you a context-free grammar and a string, can you tell me whether the grammar generates the string? This is p-complete, and therefore we shouldn't expect transformers to be able to solve this in-context task in general or express it. And finally, this is not p-complete, but it's likely a hard problem in P, testing if a number is prime. It's not known to be p-complete, but I'm putting it in here because it's likely in the upper regions of P. We can kind of obtain by a similar line of reasoning that this is likely not expressible by transformers either. Yeah.
In your diagram, you have dash lines and solid lines. Do the dash lines represent non-known or like unknown exclusions?
Yeah, these are separations that are conjectures, basically. Yeah. Okay. Okay, so in practice, we can evaluate models on some of these tasks, and we did this with ChatGPT and GPT-4. And I guess here, primality testing and graph connectivity are shown. And I guess at the time, these models would, even on very simple instances of these problems, models would answer incorrectly a lot of the time, which is the results shown by this plot. So that brings me to the last part of the talk, which is how to overcome some of the expressivity limitations of transformers. Actually, maybe I'll pause for questions quickly. Any questions before I move on? Yes. How large of a number? That's a good question. I was not first author on the paper, so I'm not sure. It wasn't like massive primes. Maybe like, I would guess like 5 to 7 digits, maybe less. But I would guess the models now do better than they did at the time also. Yeah.
In some sense, all these problems, like you're asking whether transformers can just straightaway give the answer.
Right.
We seem very surprising, these tests, like, figure clarify where does the grammar or LP, like, it's not tasks that seem to be possible to just look at them and, figure out the answer without, a lot of work that's skilled, right? So, I mean, is this what's going on here? I mean, is it really, this is a lot to ask, right?
Yeah, 100%, especially for the p-complete problems, which are really kind of hard problems. Yeah, for the lower ones, maybe they should be able to, but I agree. One of the interesting things here is that the models actually try to give an answer in one token. So part of the argument in this paper was like, the models will say like, no, because, and then give the reasoning, rather than giving reasoning and then saying no. So if you're generating your answer before giving the reasoning, that actually puts you in the regime where you need to answer right away.
That's what I was asking some large numbers trying. So check this is like 2 and 3.
Yeah, well, I mean, you probably reason first and then give an answer rather than answering and then reasoning. But yeah, I agree that with multiple steps. I mean, I'll get to this in a second. Yeah.
So you talked a little bit about non-Boolean outputs.
Yeah.
But transformers also like have non-Boolean inputs. You thought about like arithmetic circuit models of transformers, which
Yeah. So I mean, there are connections between arithmetic circuits and TC0 over Boolean circuits. I guess we found it more convenient to just think about the inputs. Like the inputs are coming from a finite alphabet, so it's not too hard to encode them with Boolean values. So we've thought mainly in terms of Boolean inputs, but you could also go that route. And I think Simran Arora has thought about this, and I think she's presenting later in the week. Okay, I'm gonna move on for now. So how to overcome these expressivity limitations of transformers. So one very natural way to do this is using like a chain of thought, basically allowing the model to take recurrent steps before answering. So if the problem is that transformers can't express sequential computation, what if we just allow the model to operate sequentially at inference time by generating tokens and adding them back to the input before we produce an answer? So this is a strategy used in practice to like improve the reasoning power of models on different empirical benchmarks. And also theoretically, it seems like it should add some power to the model. So we showed in a paper this year that chain of thought does indeed add expressive power outside of TC0, and specifically it depends on the number of steps you allow. So for example, you could allow your model a linear number of steps in the input size. You could allow a logarithmic number or a polynomial number. And depending on which you choose, you get a different characterization. So we have a paper that gives like a generic description of like relating how much is a chain of thought step worth against like a Turing machine step. And if you know how like many steps a problem requires on a Turing machine, our results give you a way to translate that into chain of thought. So specifically, like with a linear number of chain of thought steps, transformers can start to solve some inherently sequential problems. Like we showed they can simulate automata with a linear number of steps, which is an NC1. And concurrent work showed that they can also evaluate arithmetic expressions with a linear number of steps. So clearly you're kind of breaking into NC1 and starting to be able to solve some of these NC1 complete problems. But it does seem that using chain of thought to get around reasoning issues fundamentally might require a large number of steps. So for example, with a logarithmic number of steps, we didn't have any like natural problem where that was a useful amount of computation. And only like in the linear or polynomial regime were we able to express these like more complex sequential problems. And the issue with this is that if you need a lot of chain of thought steps, that's going to be expensive because it's no longer parallelizable. So that hurts the scalability of inference to some extent, but also it hurts the scalability of pre-training. You don't want to be pre-training a model that's hard to parallelize because the throughput of how many tokens you can give per second is going to go down a lot. So yeah, I guess here's the picture of our paper on this. If you're interested, there's more information in the paper. And this last point about parallelism and scalability motivates this idea of the parallelism trade-off, which was in the title of the talk. So I think like a nice takeaway from thinking about transformers with chain of thought versus transformers without chain of thought is that without chain of thought, we have transformers that can't solve sequential problems outside TC0. But on the other hand, they can be parallelized. which is nice, and that's why like we can pre-train them at scale. And if we have transformers with chain of thought or other recurrent models like LSTMs or RNNs, they actually can solve sequential problems outside TC0. So like a basic RNN can solve permutation composition, for example, but they can't be parallelized efficiently like a transformer. And that hurts the scalability if you want to train this model on a ton of data. So because pre-training at large scale requires parallelism, there's a fundamental tension between large scale pre-training and having models with expressive power outside TC0. That's like one of the high level takeaways that we want to kind of point out from this work. Although there are solutions and ways to get around this. So one solution is to train a parallelizable model and then try to adapt that model after you pre-trained it on a bunch of data to be like to use chain of thought to be more sequential. Yeah.
Let's say NC1, which is meant to be parallelizable. That's right.
Yeah, you're anticipating my next slide, so I'll get to that. Yes, good question. Yeah.
So when you incorporate something like linear chain of thought to start solving problems that are NC1 complete or something like that, are there provable upper bounds also to that, like uniform or non-uniform? Can you conceivably be outside of, like, could you conceivably solve problems outside of P? Let's say?
You're asking. Sorry, can you repeat the question?
Yeah. So with the extension with linear chain of thought, you mentioned that you can start solving problems that are NC1 complete.
Yeah.
Is there an upper bound to that model as well? Like, is it conceivable that you might be solving problems that are like outside of NP? Let's say?
You wouldn't be able to solve problems outside of NP. So we have an actual upper bound in the paper. We have two actually. They're not tight, but we have like rough upper and lower bounds. So I mean, I guess one easy upper bound is like, because a transformer runs in quadratic time, you're not going to be able to do much more than like, yeah, t squared. Yeah. Okay, move on. So another way we can think about overcoming the limitations of models is via different architectures. And that actually motivated us to think about some of these new architectures that have been proposed as transformer alternatives, like state-space models. So state-space models are a recurrent alternative to transformers. You can think about them as like a modern version of recurrent neural networks that are actually more parallelizable to train. That's like one of the benefits. And I guess because these models look recurrent, but also are practically parallelizable, we were wondering how they kind of lie on this trade-off between expressivity and parallelism. And we actually showed that current SSMs, so for example, S4 and Mamba, which you may have heard about, can only solve problems in TC0. So they have similar issues to transformers. But it's actually possible to minimally change SSMs so they can start to solve problems in NC1. And the intuition for this is that the algorithm that's used to make state-space models run efficiently is actually really similar to this NC1 style log depth, like permutation composition algorithm. So if you change the architecture a little bit, you can kind of take advantage of that, and you can express things that on hardware require log depth. Yeah, so like in some sense, these models being in TC0 is like artificially limiting. On hardware, they take basically log n depth, so we might as well make them more expressive to actually take advantage of that log n depth. So if you're interested in this idea, we talk about this in this paper called The Illusion of State in State-Space Models that came out this year. Okay, so with that, I'm just going to wrap up quickly. So I guess the high-level takeaway from this line of research, or one of the takeaways, is that transformers, if we use them as classifiers without any chain of thought, can only express parallelizable problems, formally problems in this class TC0. And thus, transformers can't express inherently sequential computation. And this includes recognizing regular languages, evaluating compositional formulas, and solving graph connectivity questions, among many other problems that are shown to be complete for different classes within P. And finally, there's this idea of a parallelism trade-off. So in some sense, attention is not all you need, or parallelizable computation is not all you need if you want to solve sequential reasoning problems. And to get around this, we can add recurrence to the model via chain of thought. And this adds expressivity, but it hurts scalability. So it's important to do it in the right way where you can still benefit from pre-training parallelism. And also, transformers don't seem to optimize the expressivity parallelism trade-off. So there's potential to have architectures that are just as practically parallelizable as transformers, but actually do have more expressive power, which I think is an exciting direction for future work. So, thanks. Yes.
Or WKB at all?
Like, that's a linear attention thing, or am I?
It's a second RNN style thing that performs similarly to transformers.
Yeah, we don't have any results about that. I think that probably you could show that. I know my collaborator was thinking about this. It might be in TC0, but we don't have a result.
Okay.
Yeah.
Yes. So do you know that transformers don't optimize the trade-off because the architecture you were the expanded like S4 model architecture we were looking at previously strictly better than the transformer?
It's not strictly better. It can express some problems that transformers cannot, but also transformers can do things that model can't. So I think there's some kind of incomparability, and I guess separate to this idea, mixing transformers and state space models might be interesting because you might get complementary strengths. But the sense in which they don't optimize the trade-off is just that they can't express problems in NC1, but in practice, hardware is basically like NC1. We're running these models in log depth. Yeah.
And I'm curious also about these space models. You use some intuition about how they avoid the issues with RNNs and how they can, because RNNs are also in some sense, for the state.
Yeah. So I guess state space models has a very specific meaning in the ML context, which is that you have basically a linear RNN, so you don't have a nonlinearity when you update the state. And as a result of this, you can parallelize the state computation using what's called the associative scan algorithm. So similar to how Bingbin showed you could simulate a finite state machine with a binary tree, you can build out a binary tree that leverages the associativity of the state update to compute all the states in parallel in sublinear time. Yeah. Yes.
So you're talking about expressivity here. In practice, do you generally find that if it's expressible, if you scale up enough, then the optimization will find it, or is there some interesting things you have about optimization? Just experiments.
Yeah, maybe other people would have more to say about this than me. I think there definitely is a gap in some cases between expressivity and learning. So for example, parity is one function that's hard to learn, but possible to express under different definitions of expressivity. So I think we've abstracted away learning because we can show that there are things that even if we don't care about learning, models can't do, but also there are things that models can't do, which theoretically are probably expressible.
Yeah. You mentioned a little bit about the gap between expressivity and learning. I'm curious if you have any thoughts about the gap between verifiability and provability in programs that exist. Because I'm kind of curious, your different ways to witness these things that it can't represent, and it seems in practice that it seems like, well, even these models that are very coarse approximations could, probabilistic heuristic for some types of proofs. So, so if you could comment on
I'm not sure I understand the question. What would be the goal of?
So in Ming-Ming's talk, he talked about using these toy problems as kind of to understand, get an intuition about more complex problems. But if you have a recognizer for the problem class, if you can very quickly run, then why not just use that to constrain models out?
Yeah, maybe we could talk after. I don't fully understand. Sorry. Yes. Yeah.
I just want to add that you can prove actually that loading step of COT will not go beyond TC0 because you can just enumerate them in parallel with polynomial mini processes and verify them in the end.
Actually, that's a good point. Yeah, that makes sense at a high level. I hadn't thought of that. Yeah.
We'll take the rest of the questions to the lunch, and we'll be back in 3 p.m. So thank you, well, again.